Hello, friends. Welcome to the fluid mechanics class. In today's lecture, we will discuss on the introduction to fluid dynamics. More importantly, what are the forces that are considered acting on a fluid body? And out of them, what are the important forces which we consider? And then from there, what is the governing equation for the fluid dynamics? And from the governing equation, how we are going to derive the Euler's equations of motion, which is our important aspect today. And then from there, how to move towards the one of the fundamental equations of fluid mechanics, the Bernoulli's equation. So this is what today we will discuss. But our lecture today is limited to only the derivation of Euler's equations of motion. And then in the next class, we integrate that Euler's equations of motion and then get the Bernoulli's equation. So first, what is fluid dynamics? Fluid dynamics is nothing but what are the forces that are acting on the fluid which is in motion. There are several forces, and these forces, what are they? That is first aspect. And always the forces are involved, or the forces results in the energy changes. And how to calculate the energies from the forces. So this is what about which we are talking about, or which we are discussing about in fluid dynamics. But broadly, the forces that are acting on a fluid body can be classified under three headings. One is the body force, second one is the surface force, third one is line force. The force which is proportional to the volume of the body is called as body force. The examples are weight and centrifugal force. The weight is mass into acceleration due to gravity. Wherever the mass is involved, how can we get the mass? Mass is equal to mass density into volume. So that's why wherever mass is involved, there the volume is automatically involved. So the forces which are proportional to the volume of the body are called as body forces. The forces which are proportional to the area of the fluid body, we call it as surface forces. The best examples are pressure force, shear force. These are all the surface forces. But there is only one line force which we consider in fluid mechanics. That line force is basic surface tension force. Means forces which are proportional to the length of the body is what we call length of the fluid body. Sorry, the length of the fluid body are called as the line forces. So these are the first three things. And then again, what are the various forces? This is broad classification. But if we look into what are the various forces that can act on a fluid body, if I take it, there are six forces which that can act on any fluid body. Number one is the gravity force, mass into acceleration due to gravity, mg. Then the second one is the pressure force. It is nothing but the pressure intensity into area, that is pressure force. Third one is the viscous force. Viscous force is nothing but the shear force, the tangential force, and it is equal to the shear stress into area, and the shear stress is equal to mu into v by y into area. The fourth one is the turbulent forces, or force due to turbulence, force due to thorough mixing of fluid particles inside the fluid, that is flowing fluid, is what we call it as turbulent forces. The fifth one is surface tension force. Surface tension force is again the line force, which is mainly due to the cohesion. The fluid, what you call it as the interface of the liquid and the gas, or the liquid and the air, the water and air interface. It acts as a membrane due to basically this surface tension force. So that is the fifth one. The sixth one is compressibility force, which is also called as the elastic force. And this elastic force is due to the compressibility of the fluid flow. That is, generally we consider these elastic forces in terms of only when we are aerodynamics. The moment you go, you can do it. And see, in the entire fluid mechanics, there is only one chapter where we call it as the water hammer. There only these compressibility effects are being considered. Apart from that, at no point we consider these compressibility forces. So we assume the fluid is incompressible. And at the same time, these surface tension forces are also negligible. So naturally, these 5 and 6 surface tension force and compressibility forces are negligible. Hence, actually, these two forces are not considered in the flow analysis in fluid mechanics. Coming to the next one, the turbulent force. The turbulent force is also not generally for all the cases we have. We only at this level, we won't consider it. If at all the turbulent effect has to be taken in any of the specific cases, we consider the effect of it at those places, but not in general. Similarly, the viscous forces also we don't consider them at this stage, because the effect of viscosity is only at limited cases we find it, and those limited cases we use that viscous force term also. But generally, when we are dealing as a civil engineer with water, the viscosity of water is so small that you can start with neglecting it, and only you can consider it in wherever the specific cases are there in that. So now finally, what are the forces that we are considering are only the gravity force and the pressure force. These are the only two forces which we are considering. But before going to that, let me explain actually what is the governing law for the fluid dynamics. The governing law for the fluid dynamics is the Newton's second law of motion. What Newton's second law of motion states: force is equal to mass into acceleration. To be precise, it is the net force acting on the fluid body in any direction is equal to mass into acceleration in that direction. If you take x, y, z directions, so it is sigma fx, which is the net force in x direction, is equal to mass into acceleration in the x direction. So that's how we consider in y and z directions also. So now if I go if I move forward in the same way, we can write actually sigma. If we write, so if I take it, so in the x direction, what are the various forces? If I take it, this is sigma fx is equal to gravity force component, pressure force component, viscous force component, then turbulent force component, surface tension force component, elastic. Just to make you to understand what are the forces, this is mass into acceleration in the x direction. So then similarly you can write in y direction and z direction. Just now I mentioned that the surface tension and elastic forces are insignificant in our fluid mechanics course. So that's why if I consider the remaining four forces, what are the remaining four forces? The gravity force, pressure force, viscous force, turbulent force. If I consider these four forces, then these equations of motion are called as Reynolds equations of motion. Please remember, in the Reynolds equations of motion, we consider gravity force, pressure force, viscous force, turbulent force. These are the four forces which we can consider. Then actually, if I already, as I mentioned, if turbulent forces are also neglected, then basically the remaining three forces are gravity force, pressure force, viscous force. If you consider these three forces, then it becomes Navier-Stokes equations of motion. So in the Navier-Stokes equations of motion, we consider only gravity force, pressure force, and viscous force. That is the, but at second year level, this level, we will not go into Navier-Stokes equations of motion, but only remember that the Navier-Stokes of equations of motion considers gravity force, pressure force, and viscous force. So this is the next. And what are the real things that which we are considering now at this level is only the, if the viscous forces are negligible, that means when the viscous forces are negligible, only when the fluid is ideal fluid, you can neglect viscous forces. In such a case, the net force acting on any fluid body is equal to the gravity force and pressure forces. This summation, and it is equal to mass into acceleration in that direction. So that's what we have shown here. So next, if I take it, so here AZ. So this is how these three directions. So now this is called as Euler's equations of motion. Euler's equations of motion broadly says that the forces considered that are only two forces. One is the gravity force, the other one is the pressure force. So taking there, I am going to analyze now what are the Euler's equations of motion. So if I take what are the Euler's equations of motion, if I take it, then so if you see, gravity force and pressure forces are only considered. The moment I say gravity force and pressure force is considered, you can clearly take it. It is applicable to only non-viscous fluid flow. That means viscosity is zero. That means it is applicable to ideal fluid flow. Now what I have to take? When I am deriving the equation in three-dimensional Cartesian coordinates, I have taken a three-dimensional element in the fluid body. This three-dimensional element, which is, for example, its sizes are delta x actually, and y direction delta y, and z direction delta z. So it's the element size is delta x, delta y, delta z. But the moment I have written delta x, delta y, delta z signifies that the element is so small, very, 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 very small actually. Now what I will do, basically, I calculate what is the net force in the x direction, net force in the y direction, net force in the z direction. So this is the thing which I will consider actually. Suppose net force in the x direction, if ask what are the phases actually through which the forces will be there. One, the, for example, if I take it, PQRS is one phase, P dash Q dash R dash S dash is the other phase. Similarly, if you want in y direction is the front one which you are seeing and the back one which you are seeing. That is QQ dash R, and the back one is PP dash S. And if suppose in the Z direction, if you take it, bottom one and top one, bottom one is PQQ dash P dash, and the top one is R dash S. So this is how you need to consider the phases and what are the forces that are considered. So now how I started, let rho be, for example, UVW be the velocity components in x, y, z directions. I have taken the origin as P is the origin I have taken. From there, now you see whether the phase is on the left side or right side. Like that you should see it so that it will be positive or negative. Then second thing is, I already mentioned there are only two forces considered. One is the gravity force component. The other one is the pressure force component. How I calculate the gravity force component and how I calculate the pressure force component. When I take it, the first thing is the gravity force component. You all know that the gravity force component is only in the vertical direction. But here I am writing let x, y, z be the gravity force components per unit mass in x, y, z directions. Why I have taken like that instead of taking only in the vertical direction, that means z direction? The reason being, when I am deriving a differential equation, I am deriving a general equation. So when I am deriving a general equation, I am keeping the terms intact. Only when I come to the conclusion, there I will conclude that the remaining two directions, it will not be there, only it will be in the vertical direction. So keeping that in mind, so let capital X, capital Y, capital Z be the gravity force components in per unit mass in X, Y, Z directions. Right? Similarly, the pressure intensity. I have taken the pressure intensity also. Pressure intensity I am calculating. Before calculating the pressure intensity, how I calculate the pressure intensity, I will show. But total gravity force components I have shown here. You can see it. What is the mass of the fluid element? Mass of the fluid element, how you will get it? You have to get the first volume. What is the volume? This delta X, delta Y, delta Z is the volume. This volume multiplied by the mass density will give you mass. So that's how you will get the mass. So what I mentioned, what is the gravity force in X direction? X is the gravity force per unit mass. Into mass, if I put X into rho delta X, delta Y, delta Z. Similarly, in the other two directions. Now coming to the pressure force. So pressure force, actually there are two phases in the X direction. One is PQRS, the other one is P dash Q dash, sorry, P dash Q dash R dash S dash. PQRS is on the left face and P dash Q dash R dash S dash in the is the right, on the right side. Now what is the pressure force? P is the intensity at any point. P is the intensity of pressure at any point. You can take with at this place the pressure intensity is P. That's what I have taken here. The pressure intensity is P here. So at any place on this face, the pressure intensity is P only. Why P only? Because this element size is very small. P delta Y delta Z. This element size is so small that we assume the pressure distribution is uniform on the entire face. When the pressure distribution is uniform, what is the pressure force? Pressure force is equal to pressure intensity into area. So P into delta Y delta Z. That is how I have written. Then what is the pressure force on the right side to keep the element in equilibrium? So that is it is P plus or minus something. That is what you should understand. What that plus or minus? Because this this face is on the right side of it, on the positive side of the x-axis. That means x we have taken here. It is on the positive side. So I put plus P plus something. What is that something? From here, from this face to this face, the distance is delta x. What is the change of pressure per unit distance? It is dou p by dou x. If dou p by dou x is the change of pressure per unit distance, then what is the change of pressure in delta x distance? That is dou p by dou x into delta x. So now what is the total pressure intensity on face P dash Q dash R dash S dash? Pressure intensity is P plus dou P by dou X into delta X. Now, what is the pressure force? Pressure intensity into area. So, what is that? P plus dou P by dou X into delta X into delta Y delta Z. So, now what I am, we are interested, what is the net pressure force in the X direction? Originally on the left face, it is P delta Y delta Z, and on the right face, it is P plus dou P by dou X into delta X into delta Y delta Z. So now what is the net pressure force? That means directions are different. So therefore, if we put it P delta Y delta Z minus P delta Y delta Z minus dou P by dou X into delta X delta Y delta Z. So this P delta Y delta Z minus P delta Y delta Z cancels each other, and the remaining is only minus dou P by dou X into delta X delta Y delta Z. Similarly, in the other two directions, Y and Z direction also, we can write it as minus dou P by dou Y into delta X delta Y delta Z. Z direction also minus dou P by dou Z into delta X delta Y delta Z. So this is the net pressure force. Now what is the According to Newton's second law of motion, the net force in x direction is equal to mass into acceleration in x direction. So, therefore, first one is the gravity force component in x direction, x into rho delta x delta y delta z, minus pressure force component in the x direction, minus dou p by dou x into delta x delta y delta z. So, this is the net pressure force on the fluid element is equal to mass into acceleration. What is mass is equal to volume is delta x delta y delta z into mass density rho delta x delta y delta z becomes the mass. So rho delta x delta y delta z into ax. So and again here itself I wish to mention to you we are considering the fluid is incompressible. That therefore when the fluid is incompressible, what happens to mass density? The compressibility effect in terms of fluid mechanics is if the fluid is incompressible, rho becomes constant, mass density becomes constant. It is just a number. So that is why rho is equal to constant. So whether it is inside the derivative or outside the derivative, it really did not make any change. So it is like a volume term as far as the mathematics is concerned. So now what I have done, x into rho delta x delta y delta z minus dou p by dou x into delta x delta y delta z is equal to mass into rho delta x delta y delta z into ax. So throughout I am dividing by rho delta x delta y delta z throughout. Each term I am dividing it by rho delta x delta y delta z. If we divide each term by rho delta x delta y delta z, in the first term all that will go, remaining is only x. In the second term, it is only delta x delta y delta z we have in the numerator, but in the denominator we are going to write rho into delta x delta y delta z. So only remaining is rho is there. So that is why minus 1 by rho dou p by dou x is equal to, again the whole term will cancel, only ax remains. So finally what we got after dividing it with rho delta x delta y delta z, the whole equation, x minus 1 by rho into dou p by dou x is equal to ax. Similarly, y minus 1 by rho dou p by dou y is equal to ay. Z minus 1 by rho dou p by dou z is equal to az. And this is called Euler's equations of motion. These three equations are Euler's equations of motion. A little bit elaboration of these three, we will do it. You all know what is ax. In the fluid kinematics we have done it. Ax is equal to u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou w by dou t. Similarly az. So finally we have written ax, y, ay, az, replacing them with the original terminologies. That is the velocities in the velocities and change of velocities with respect to space and time in xyz directions. So therefore x minus 1 by rho dou p by dou x is equal to ax is equal to u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. Similarly the other two. Now this is called as Euler's equations of motion, and you are supposed to write up to this. So now what we have done, if I just remind you once again, I have taken the governing equation, Newton's second law of motion. I have described the various forces, only considering gravity, pressure only I considered, rest I we did not consider. So considering these two forces, if I derive some analysis, do some analysis and derive some equations, and that's where we got Euler's equations of motion. But our aim is not to derive the Euler's equations of motion. Euler's equations of motion is not our goal. Our goal is another thing. So what we need to do, if we integrate these Euler's equations of motion, then we get the equations of energy which we require. That energy equation is the Bernoulli's equation. This is what we want. So in today's lecture, we have considered only up to this point, that is only starting from Newton's second law of motion, explaining the forces, considering pressure and gravity forces, deriving Euler's equations of motion. So to that, I will stop here. But in the next class, I integrate that Euler's equations of motion, and then from there, I get the Bernoulli's equation. And this Bernoulli's equation is the energy equation. Kindly remember that in the beginning I mentioned there are three fundamental equations of fluid mechanics: continuity equation, Bernoulli's equation, impulse momentum equation. The continuity equation I have derived in fluid kinematics. And in fluid dynamics, we derive first Bernoulli's equation and then impulse momentum equation. All our fluid mechanics flow applications are relied only on these three. Number one is continuity, Bernoulli's, impulse momentum. Mostly the first two, continuity and Bernoulli's equations. These are the two fundamental equations. If you want to solve any problem, these equations you should know thoroughly. There we will stop, and thank you very much for your patient viewing and listening. And let us meet in the next class with starting with the Euler's equations of motion and integrating it, getting the Bernoulli's equation. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.